External, on-stream, and internal inspection: what, why, where, when, and how, a comprehensive overview of inspection methods and purposes. Inspection of pressure equipment, objectives of the presentation: what is inspection, types of inspection. Pressure equipment inspection is a foundational element of asset integrity management across industries such as oil and gas, petrochemical, and power generation. This introductory content explains that inspection encompasses a structured and disciplined approach aimed at ensuring that critical equipment, including pressure vessels, piping systems, and storage tanks, remain safe, functional, and capable of operating as designed. Inspections are governed by internationally recognized engineering standards, such as API 510, API 570, API 653, and ASME codes, which define the minimum acceptable practices for assessing equipment condition. The introduction highlights the interconnection between external, on-stream, and internal inspections, and how these inspection categories collectively support the early identification of degradation mechanisms, prevention of catastrophic failures, reduction of unplanned downtime, and improvement of reliability. This slide sets the stage for deeper exploration by emphasizing that inspection is not simply visual checking, it is a systematic, engineering-based discipline that uses advanced technologies, structured methodologies, and evidence-based decision-making. The content also underscores how inspection contributes to regulatory compliance, environmental protection, and personnel safety, making it a non-negotiable requirement in asset-intensive industries. This section lays out the purpose and scope of the full presentation by detailing the key learning objectives. It explains that the session aims to clarify what external, on-stream, and internal inspections are, why each type is necessary, where they are performed within industrial facilities, when they should be carried out based on regulatory and condition-driven triggers, and how they are executed using established inspection technologies and engineering methodologies. The objective is to provide both foundational knowledge and practical engineering insight, enabling professionals to understand not only the differences between inspection types but also how they interrelate within a complete mechanical integrity program. This slide explains that participants will gain a deeper understanding of degradation mechanisms, inspection planning, operational considerations, shutdown strategies, and the integration of inspection activities into risk-based inspection (RBI) frameworks. Ultimately, the presentation aims to strengthen engineering judgment, support informed decision-making, and enhance the reliability and safety of industrial operations. Inspection, in the engineering context, is the systematic process of examining equipment to assess its physical condition, identify degradation, and evaluate its suitability for continued service. This slide explains that inspections are not merely reactive, they are proactive tools that help engineers identify early signs of deterioration such as corrosion, cracking, deformation, erosion, or operational anomalies. The content emphasizes that inspection is essential for confirming the fitness for service of equipment, ensuring compliance with legal and regulatory codes, and maintaining safe operation. It also explains that the inspection discipline incorporates both qualitative, visual observation, condition monitoring feedback, and quantitative methods, NDT measurements, advanced diagnostic technologies. Beyond condition assessment, inspection plays a crucial role in life extension strategies, integrity risk reduction, and safe work planning, making it a key pillar of modern reliability-centered maintenance programs. This section provides an overview of the three major categories of inspection used in pressure equipment integrity management: external, on-stream, and internal. It explains that external inspection focuses on evaluating outside surfaces and components while equipment remains accessible externally. On-stream inspection involves the use of non-destructive testing, NDT, technologies while equipment remains in operation, and internal inspection requires opening, cleaning, and physically accessing the inside of equipment during shutdown. These categories are not interchangeable but complementary, each addressing different inspection challenges and degradation types. For example, external checks excel at spotting coating failures, external corrosion, and leaks, while on-stream inspection captures wall thickness trends and thermal anomalies, and internal inspection exposes internal corrosion, erosion, and mechanical defects that cannot be detected externally. The content further elaborates that optimal plant reliability depends on correctly selecting and sequencing these inspection types in alignment with risk, operational constraints, and equipment criticality. What is external inspection? Why perform external inspection? Where external inspection is performed, when external inspection should be conducted, how external inspection is performed. External inspection refers to the assessment of equipment surfaces, structures, and attachments that are accessible without opening or shutting down the equipment. This slide explains that external inspection typically includes visual surveys, surface condition evaluations, and secondary diagnostic checks that can be performed while the equipment remains online. The purpose of this inspection type is to identify early evidence of external corrosion, coating breakdown, deformation, leaks, vibration-induced damage, and structural abnormalities. External inspection acts as the first line of defense in identifying deteriorating conditions because external surfaces often provide visible clues about internal conditions. Though considered less intrusive, external inspections are essential for continuous equipment health monitoring and play a major role in detecting emergent issues before they escalate into significant failures. External inspections also provide key data that feed into RBI programs and help adjust inspection intervals. This section explains the engineering rationale behind performing external inspections, emphasizing their importance in detecting visible degradation and operational anomalies. External inspections are crucial for identifying corrosion under insulation, coating failures, environmental degradation, structural distortion, leaking flanges, loose supports, and thermal discoloration. Early detection prevents small issues from escalating into high-consequence failures, thus protecting personnel's safety and ensuring environmental compliance. The content also highlights how external inspections reduce overall maintenance costs by enabling predictive and preventive maintenance and reducing unplanned downtime. They also support regulatory requirements, insurance obligations, and audits by demonstrating consistent equipment monitoring. External inspections further help validate corrosion models, ensure the effectiveness of protective coatings, and monitor areas exposed to weathering or process-related stresses. Through regular external checks, organizations can maintain asset reliability and optimize long-term equipment performance. External inspections are applicable to a wide range of equipment components throughout industrial facilities. This slide explains that they are performed on pressure vessels, exposed piping systems, supports, hangers, insulation systems, weld seams, structural platforms, and associated attachments. The content elaborates that any surface accessible without intrusive access qualifies for external inspection. In tank farms, external inspection includes checking shell courses, roof structures, foundations, and settlement conditions. In piping networks, inspectors focus on pipe racks, elbows, flanges, and dead legs. In reactors and heat exchangers, external inspection includes nozzles, supports, ladders, fireproofing, and refractory systems. This slide emphasizes that external inspection coverage is broad and must be systematic, ensuring all high-risk and high-exposure areas are examined regularly. This content explains the timing criteria for conducting external inspections, emphasizing that they occur during routine operator rounds, scheduled inspection intervals, and after unusual operational events. External inspections are conducted more frequently than internal inspections due to their non-invasive nature. Codes such as API 570, API 510, and API 653 guide the minimum intervals. External inspections should also be repeated after incidents such as process upsets, leaks, vibrations, impacts, or environmental events like heavy rain or flooding. RBI may extend or shorten inspection intervals based on observed corrosion rates, operating conditions, or degradation patterns. Additionally, newly commissioned equipment undergoes external inspection as part of baseline condition documentation. This timing strategy ensures continuous condition monitoring and supports proactive intervention. This slide explains the practical steps and methods used to conduct external inspections. Inspectors typically begin with visual examination using the naked eye or magnifiers, observing for discoloration, corrosion, leaks, bulging, vibration marks, or coating failure. Additional tools often employed include digital cameras, drones, binoculars, portable lighting, and inspection mirrors to access hard-to-reach areas. Hammer testing may be performed on structural components to identify delamination or internal voids. Inspectors also evaluate insulation condition, support integrity, fireproofing adhesion, and flange gasket leakage indicators. Documentation involves capturing photographs, recording measurements, and updating condition monitoring records. The slide emphasizes the need for qualified inspectors trained in visual examination per API, ASNT, or equivalent competency programs. This ensures that observations are technically sound and traceable. What is on-stream inspection? Why perform on-stream inspection? Where on-stream inspection is performed, when on-stream inspection should be conducted, how on-stream inspection is performed. On-stream inspection involves evaluating the condition of equipment while it remains in operation and under pressure. This slide details the importance of performing inspections without requiring shutdowns, thereby avoiding production interruption. These inspections utilize advanced non-destructive testing, NDT, methods such as ultrasonic thickness measurements, radiography, guided wave testing, thermography, and acoustic emission monitoring. On-stream inspection enables engineers to detect wall thinning, analyze corrosion trends, identify thermal anomalies, and detect mechanical degradation such as vibration-induced cracking. It is particularly useful for high-risk or continuously operating units where shutdowns are costly or infrequent. This form of inspection provides real-time asset condition data and supports predictive maintenance strategies, enhancing safety and operational reliability. This slide highlights the engineering motivations for conducting on-stream inspections. On-stream inspection allows continuous monitoring of equipment health, minimizing the risk of unexpected failures. It is essential for tracking corrosion rates in real time, assessing the progression of known damage mechanisms, and validating inspection models used in RBI. On-stream inspection also reduces maintenance costs and maximizes production uptime by minimizing the need for intrusive inspections. It ensures regulatory compliance when equipment cannot be taken out of service frequently. On-stream inspections also help operators detect conditions such as hot spots, flow-accelerated corrosion, leaks, and mechanical vibration issues while the system is still operating, enabling early intervention and improved reliability. This content identifies common equipment and locations where on-stream inspection is used. These include high-risk piping circuits, corrosion loops, boilers, heat exchangers, furnaces, reactors, and process units with high operating temperatures or pressures. On-stream inspection is particularly valuable in systems where corrosion is active or where degradation is likely to progress rapidly. Inspectors focus on elbows, T's, nozzles, welds, injection points, dead legs, and areas with turbulent or erosive flow. The slide also explains that elevated equipment or insulated components may require supporting technologies such as rope access, drones, or infrared cameras to identify hidden damage. On-stream inspection is applied selectively in high-risk or critical systems where monitoring is essential to avoid catastrophic failure. This slide explains that on-stream inspections are performed between major shutdowns and are scheduled based on corrosion rates, equipment criticality, and RBI methodologies. They are also required after significant process changes such as feedstock variation, temperature shifts, pressure changes, or flow alterations, which may accelerate degradation. On-stream inspections are sometimes triggered by abnormal operating events, alarms, or unexpected vibration readings. The frequency of these inspections varies widely depending on the damage mechanism and the expected rate of deterioration. For example, systems operating under high corrosion rates may require yearly or quarterly monitoring, while more stable systems may be monitored less frequently. On-stream inspection enables real-time adjustment of maintenance and shutdown plans based on actual equipment condition. This section provides a detailed explanation of the technologies and procedures used in on-stream inspection. Techniques include ultrasonic thickness measurement, UT, for wall thinning, infrared thermography for hotspot detection, radiography for internal flaw identification, and acoustic emission for detecting crack growth. Engineers may also use vibration analysis tools, corrosion probes, remote monitoring sensors, and real-time data acquisition systems. On-stream inspection requires strict safety planning, especially when inspecting hot or pressurized equipment. Inspectors often use scaffolding, rope access, or robotic crawlers to reach high or hazardous areas. The collected data is integrated into equipment history files and corrosion monitoring databases, ensuring accurate trend analysis and life prediction. The slide emphasizes that only trained NDT professionals should perform on-stream inspection. What is internal inspection? Why perform internal inspection? Where internal inspection is performed, when internal inspection should be conducted, how internal inspection is performed. Internal inspection is the most detailed form of equipment examination and requires shutdown, isolation, opening, and cleaning of the vessel or piping system. This slide explains that internal inspection allows direct visualization and measurement of internal surfaces, welds, trays, internals, baffles, refractory linings, and other features not accessible externally. Internal inspection provides high-quality data on degradation mechanisms such as internal corrosion, erosion, stress corrosion cracking, pitting, deposit formation, and refractory damage. This inspection type is typically governed by strict safety requirements including confined space entry procedures, gas testing, ventilation, and isolation controls. Internal inspection is essential for validating corrosion models, determining remaining life, and confirming fitness for service under API 579 frameworks. This slide explains that internal inspection provides a level of detail and certainty unmatched by external or on-stream methods. Internal inspections allow engineers to accurately assess internal corrosion morphology, detect cracks, identify erosive wear, evaluate weld quality, measure pitting depth, and inspect internals such as trays, demisters, and baffles. These inspections confirm or challenge previous predictions made by RBI models and corrosion monitoring tools. Internal inspection is also required for statutory compliance, especially for pressure vessels governed by local regulations. The content further emphasizes that internal inspection results frequently guide future inspection planning, determine the need for repairs or replacements, and influence long-term asset management decisions. Without periodic internal inspection, many hidden degradation mechanisms would remain undetected until failure. Internal inspections are performed on pressure vessels, columns, heat exchangers, reactors, separators, and tanks. The slide explains that each equipment type has specific internal components requiring detailed assessment. For example, pressure vessels require internal weld inspection, corrosion mapping, and nozzle evaluation, while columns require tray and packing assessment. Tanks require bottom plate inspection, corrosion mapping, and settlement evaluation. Internal inspection may also apply to critical piping systems where internal corrosion is suspected, especially in dead legs or flow-restricted areas. This slide emphasizes that internal inspection coverage must be comprehensive and planned based on expected damage mechanisms and areas of high risk. This content explains that internal inspections are typically scheduled during major shutdowns or turnarounds due to their intrusive nature. Codes such as API 510 and API 653 define the minimum intervals for internal inspection, although RBI may extend or reduce these intervals based on risk. Internal inspection may also be required after severe service events, such as high-temperature excursions, process upsets, or suspected corrosion failures. This slide further highlights that internal inspections must be carefully planned to ensure cleaning and access preparation, removal of internals if necessary, and safe entry conditions. The timing of internal inspection plays a critical role in long-term integrity planning and shutdown optimization. Internal inspections involve several sequential steps beginning with equipment isolation, depressurization, draining, cleaning, and purging. Once safe entry conditions are confirmed, inspectors conduct internal visual surveys using flashlights, borescopes, high-resolution cameras, and drones designed for confined spaces. NDT techniques such as magnetic particle testing, MT, dye penetrant testing, PT, ultrasonic shear wave testing, and hardness testing may be applied internally. Inspectors measure corrosion, pitting, and erosion using pit gauges and ultrasonic mapping devices. Structural components such as trays, baffles, demister pads, and refractory linings are evaluated for mechanical integrity. Detailed documentation, including sketches, photographs, defect logs, and measurement records, is essential. The slide emphasizes that internal inspection requires trained and certified professionals due to its technical and safety complexity. Advanced Inspection Integration, Risk-Based Inspection, RBI, Typical Inspection Workflow, Common Inspection Findings. Risk-Based Inspection, RBI, is a methodology that prioritizes inspection activities based on the likelihood and consequences of equipment failure. This slide explains that RBI integrates data from external, on-stream, and internal inspections to quantify the risk associated with each asset. Using this risk assessment, engineers can optimize inspection frequency, scope, and methods, allocating more resources to high-risk equipment and reducing effort on low-risk components. The content highlights that RBI considers process conditions, degradation mechanisms, historical corrosion rates, failure consequences, and uncertainty factors. RBI programs support regulatory compliance, improve safety outcomes, reduce maintenance costs, and enhance operational reliability. This section emphasizes that effective RBI requires accurate and updated inspection data. This slide describes the typical workflow used in inspection and integrity management. It begins with identifying expected damage mechanisms based on process parameters, fluid chemistry, temperature, and material selection. Engineers then select the appropriate inspection type and NDT method. Field inspection activities are conducted, and the collected data is analyzed to evaluate equipment condition and determine whether it meets fitness for service criteria. Findings are incorporated into reliability models, and inspection intervals are updated based on observed conditions. Engineering recommendations, such as repairs, replacements, or monitoring adjustments, are issued. This systematic workflow ensures traceable, evidence-based decisions and supports long-term asset integrity planning. This section discusses typical degradation mechanisms identified during inspections. Common findings include general corrosion, localized pitting, erosion at high-velocity areas, stress corrosion cracking in susceptible materials, weld defects, coating failure, thermal distortion, and mechanical damage from vibration or poor support conditions. The slide explains that each mechanism has distinct characteristics and severity implications. Understanding these findings helps engineers correctly classify defect severity, estimate remaining life, and determine the appropriate corrective actions. This content emphasizes that consistent detection and understanding of degradation patterns are essential for predicting long-term equipment behavior. Summary of inspection concepts, closing, and next steps. This slide summarizes the key insights from the presentation, reinforcing that external, on-stream, and internal inspections offer complementary perspectives essential for ensuring the safe operation of industrial equipment. External inspections provide early detection of visible degradation, on-stream inspections deliver real-time condition monitoring, and internal inspections reveal detailed information about internal surfaces and hidden failure mechanisms. The content emphasizes the importance of understanding what, why, where, when, and how each inspection type is conducted. It also reiterates the value of integrating these inspection strategies within RBI frameworks to optimize resource allocation and enhance overall asset reliability and safety. The final slide encourages participants to apply the inspection concepts learned and incorporate structured inspection planning, accurate data collection, and engineering analysis into their daily work. It highlights that effective inspection programs require collaboration among inspectors, engineers, operators, and plant management. The content emphasizes that continuous improvement, technology adoption, and adherence to engineering standards are key to maintaining mechanical integrity. The slide invites further discussion and questions, promoting knowledge sharing and ongoing learning to enhance inspection effectiveness and safety performance.